Hi all, welcome back to our discussion on atmospheric wave motion. Today we'll be discussing the zonal mean atmosphere, and we'll look at Rossby waves. So recall from last time that we talked about linearization of the nonlinear set of evolution equations. The basic process of linearization involved taking all variables and decomposing them into a mean state, here denoted by u bar, and a perturbation denoted by u prime. The basic idea is that the perturbations need to be assumed to be small relative to the mean state, and consequently the product of perturbations is doubly small when compared to the product of two mean states. Consequently, for each of the variables that are responsible for driving the equations of motion, we will need to know a mean state for these variables in order to ensure that perturbations are actually small. So this leads to the outstanding question then, what are the appropriate choices for the mean state of the atmosphere? We'll now go over basically each of the major variables associated with the evolution equations and look at how the mean state can be best parameterized. So let's start off by looking at the zonal mean zonal wind. So here examining an annual mean as well as a zonal mean of the zonal wind quantity. In particular, the zonal wind is dominated by two subtropical jets, which are located at approximately 30 degrees north and 30 degrees south at the top of the troposphere. So these zonal jets have wind speeds which can reach up to about 100 meters per second instantaneously. Over an annual mean, however, the maximum reaches closer to about 35 meters per second. Overall, this suggests that if we were to use a mean state which is simply zero background wind, that this would not be adequate in order to best represent small perturbations, since the zonal jets would then be perturbations themselves and would be very, very large relative to the mean state. Consequently, the best thing to do in this case is to choose a mean state which closely represents the zonal wind profile that we see in this image. So what is typically done is to have a u bar which is dependent not only on latitude but also dependent on height, and matching a profile very close to the one which is depicted here. For meridional wind, on the other hand, meridional wind tends to be very small relative to the zonal wind. Maximums of the meridional wind are only about between 2 and 4 meters per second in the tropical region, just to the north and south of the equator. However, elsewhere in the domain, especially in the mid-latitudes, the meridional wind is very close to zero. And consequently, having a zonal mean meridional wind equal to zero is actually a fairly good assumption, especially when compared to the mean zonal wind state that we saw on the previous slide. So consequently, it is acceptable to generally choose a mean meridional wind equal to zero. Look at mean zonal sea level pressure. Along the horizontal surface, sea level pressure is fairly constant, varying between approximately 980 hectopascal and about 1020 or 1030 hectopascal. This is very weak horizontal variation compared to variations of the pressure in the vertical direction, especially if one neglects regions around the south polar vortex, where the sea level pressures dip down to their lowest levels. Consequently, it's reasonable to assume a mean sea level pressure that is approximately constant horizontally. When accounting for the full 3D pressure, obviously pressure decays roughly exponentially in the vertical direction, and hence the usage of a constant pressure is probably not the best choice in that case. Hence we generally choose a mean pressure which is purely a function of height to account for the exponential variation in the vertical. Temperature has analogous behavior. Generally, horizontal variations in temperature are small unless considering variations on the planetary scale, that is, going between the equator and poles. However, variations in the vertical tend to be much stronger, especially over the length of the troposphere. Hence, it is common in order to again choose a mean temperature, which is approximately constant horizontally, but has strong height-dependent variation associated with it. That is, mean temperature is approximately only a function of z. Note that if one was to do perturbations on a planetary scale, this assumption may fall apart. However, for smaller scale analysis, such as purely looking at the mid-latitudes over one season, this is a fairly accurate approximation. If one was to look at temperature profile in the vertical, you can clearly see the very strong variations associated with this temperature profile, and hence the reason for choosing a temperature profile that is a function of the vertical coordinate. If we now look at potential temperature varies more strongly in the horizontal direction. However, as you get up to the upper troposphere, horizontal variations are generally small. For this case, especially for, again, analysis over a particular region or on a smaller scale, a much more reasonable approximation for the mean state is to purely choose theta as a function of the vertical coordinate z. Again, if one was to do analysis on a planetary scale, this assumption may fall apart. Alright, so now we're going to look at Rossby waves as our first examination of wave-like behavior in the atmosphere. Rossby waves have been seen previously in this lecture series, including in our analysis of mountain wave response in the vorticity section, and our look at synoptic-scale waves in the quasi-geostrophic analysis section. So Rossby waves are planetary scale waves, which pass around the whole planet with wave number of approximately 5 or 6. So these waves are particularly important for large-scale atmospheric processes and are one of the main drivers of mid-latitudinal weather, as we saw for quasi-geostrophic theory. Rossby waves, as they progress around the atmosphere, can intensify or weaken. As they intensify, they will be then responsible for the generation of baroclinicity and baroclinic instabilities. Synoptic-scale Rossby waves can be clearly seen on weather maps, here showing a mountain wave response to a westerly flow. We see the mountain wave drop southward dramatically over the Rocky Mountains and bounce back as it moves farther east. This wave pattern will then progress farther around the Earth, continuing to extend with a wavelength of approximately between 5,000 and 10,000 kilometers. Barotropic Rossby waves can be studied by looking at conservation of barotropic potential vorticity, analogous to how we analyzed mountain waves in the vorticity section. Recall that if looking at a single fluid column, this system will generally conserve absolute vorticity, assuming no stretching is present for the fluid column. This can be then written as the material derivative in the horizontal of absolute vorticity, which is equal to the sum of relative vorticity and planetary vorticity. Expanding this out in an Eulerian context, one gets partial derivative with respect to t plus u partial derivative with respect to x plus v partial derivative with respect to y as a composed operator applied to the relative vorticity plus beta times v. The planetary vorticity here being a much smaller term due to the fact that f only has variations in the meridional direction. As we talked about previously, waves need to have a restoring force associated with them. And for Rossby waves, that restoring force is the beta effect. That is the fact that Coriolis force varies as you go north and south away from a reference latitude. Consequently, one will observe that this has a response in the relative vorticity, which will then tend to cause fluid parcels to be redirected back towards their reference latitude. So we're going to try to understand barotropic Rossby waves by trying to look at a closed chain of fluid parcels which are initially aligned along a constant circle of latitude. Here we see Rossby waves as they bounce north and south away from the reference latitude. Here we have our chain of fluid parcels following along the path depicted here. In region 1, we have positive relative vorticity associated with these fluid parcels. In position 2, we have negative relative vorticity associated with these fluid parcels. The oscillation between positive and negative relative vorticity then leads to the variations which are responsible for the wave-like behavior of this particular phenomenon. So starting from conservation of absolute vorticity, we will assume that relative vorticity is equal to 0 at time t1, and that the fluid parcel has an initial displacement, meridional displacement of delta y from its original latitude. Hence, the initial absolute vorticity of the fluid parcel is equal to relative vorticity plus planetary vorticity, but since initial relative vorticity is assumed to be 0, this is purely the initial planetary vorticity. Relative vorticity at a final time is then equal to the difference in the planetary vorticities between the initial time and the final time, and then is given by negative beta times delta y. So one then observes that for northward displaced fluid parcels, that is where delta y is positive, this will lead to a negative relative vorticity. For fluid parcels which are displaced southwards, delta y will be negative, and hence there will be positive relative vorticity associated with these fluid parcels. This construction is a requirement in order to ensure wave-like behavior of the fluid parcels. For easterly flow, as we saw previously for mountain flow over for easterly flow over a mountain, it actually turns out that the wave-like character is not maintained, and one gets exponentially increasing solutions away from the reference latitude. Hence, in the easterly regime, one does not obtain wave-like behavior for these Rossby waves. Okay, we're going to compute a phase speed now. We're going to assume wave-like behavior of the meridional displacement by assuming it's of the form a times sine kx minus ct. Again, k is the horizontal wave number, and c is the phase speed in the zonal direction. Taking this displacement and using the fact that the meridional velocity is equal to the material derivative of the meridional displacement, one can then expand this out using the fact that there is a background reference zonal velocity field given by u bar, and expand this out as Ka u bar minus c all times cos kx minus ct. Relative vorticity is then given by di v di x due to the fact that we are assuming that variations of the zonal velocity are small. So taking the derivative then of the v velocity that we previously derived, one obtains minus k squared a u bar minus c times sine kx minus ct. We then use the fact that the relative vorticity at the final time is equal to minus beta times delta y, and equate these two expressions in order to obtain a final expression for the phase speed in terms of the mean background velocity, the beta parameter, and the zonal wave number k. In particular, you'll observe that the phase speed is always slower than the background mean zonal wind field. In fact, as k increases, this quantity becomes propagates even more strongly in the westward direction. In fact, for k sufficiently small, one will have actually that this second parameter is much more negative than the mean wind speed, and hence one will have a phase speed associated with these Rossby waves, which is westward propagating, that is against the mean flow field. So this perturbation induces a meridional velocity which advects the fluid parcel southwards to the west of the vorticity maximum and northwards west of the vorticity minimum. This can be seen depicted here in this figure, where we assume that fluid parcels are simply oscillating north and south. They will oscillate about this equilibrium latitude using the beta parameter as the restoring force. The phase of this will tend to propagate westwards relative to the mean flow, as is characteristic for Rossby waves. Further, the phase speed is going to be a function of the horizontal wave number k, and hence these waves are dispersive. That is, waves of different wavelengths will propagate at different speeds. We'll now go through an alternative derivation which will look at a 2D Rossby wave, that is incorporating both zonal wave number and meridional wave number. We again start with the same conservation of absolute vorticity, which is characteristic for barotropic flows on a mid-latitude and beta plane. We will now use linearization about a basic state where we have a mean zonal wind u bar and a perturbation u prime. V is again assumed to be perturbed around a zero background state. Then computing the relative vorticity, accounting for both v and u, will give you your perturbed relative vorticity zeta prime. In particular, observe that here the mean wind is assumed to be constant and hence is not incorporated into the mean vorticity field. We then define a perturbation stream function here, which is analogous to the geopotential that we saw for quasi-geostrophic theory, and basically encapsulates the fact that the flow field is assumed to be non-divergent. Using the stream function, we then have that u prime is equal to minus partial of psi prime with respect to y, and y prime is equal to partial of psi prime with respect to x. Hence, the relative vorticity field is equal to the Laplacian of the perturbation stream function. So this leads to a perturbation form of the barotropic vorticity equation, which we derived previously. And in particular, you'll notice that this is now a closed form equation in terms of only a single dependent variable, psi prime. If we now seek solutions which are wave-like, that is given by some amplitude psi times exponential of I kx plus ly minus nu t, at the end we'll pick the real part of the solution and hence obtain the phase speed associated with this wave propagation. Performing this analysis then leads to the dispersion relation, which looks like nu equal to u bar k minus beta k over kappa squared. Here kappa squared is the two-dimensional wave number vector magnitude squared, which is given by k squared plus l squared. The phase speed is then computed by dividing the frequency by k and l in order to give the components of the phase speed. So in the zonal direction, we have a phase speed which is given by u bar minus beta over kappa squared. Compare this to the previous derivation where we showed that the zonal wave speed is equal to u bar minus beta over k. Also in the meridional direction, we have a phase speed ku bar over l minus k beta over l kappa squared. We can also derive the group speed associated with barotropic Rossby waves, and the components are then given by u bar minus beta k squared minus l squared all over kappa to the fourth for in the zonal direction, and in the meridional direction 2 beta kl over kappa to the fourth. Hence we observe that Rossby waves phase speed is always westward relative to the mean flow, and that the phase speed depends inversely on the square of the horizontal wave number. Hence, we can conclude that Rossby waves are dispersive with phase speeds which increase with increasing wavelength. That is, increase with decreasing wave number. For the shortest waves, which occur for the largest values of k, the beta over k term will then be small, and hence these waves will tend to propagate with the mean transport speed. Note also that the group speed can be either eastward or westward relative to the mean flow, depending on the choice of wave numbers k and l, whereas the phase speed is always westward relative to the mean flow. So consistent with the discussion from quasi-geostrophic theory, we then observe for barotropic Rossby waves that if advection of planetary vorticity dominates over advection of relative vorticity, then the waves will tend to move westwards. That is, they will tend to regress. So for example, for k approximately equal to L and zonal wavelength of order 6,000 kilometers, the Rossby wave speed is minus 8 meters per second relative to the mean flow, using the phase speed relationship. Long Rossby waves may be stationary also if one computes the wave number at which the phase speed is exactly equal to 0. And so these will be stationary relative to the Earth's surface. And the stationary wave number can actually be computed directly from the phase speed relationship and takes the form kappa squared equals beta over u bar. Note that this actually provides a family of wave number solutions of KL pairs, all of which, if they satisfy kappa squared equals beta over u bar, will be stationary relative to the surface. So unlike phase speed, zonal group velocity may be either westward or eastward, and the direction depends on the ratio of zonal and meridional wave numbers. Stationary and most synoptic scale Rossby waves will have eastward zonal group velocities. That is, energy will tend to be propagated by Rossby waves in the eastward direction. For synoptic waves, eastward advection by mean u often dominates over westward phase propagation of Rossby waves, and so waves move eastward, but at a slower phase speed than the zonal group velocity. And finally, it's an important consequence of this result that new disturbances tend to develop downstream of existing disturbances. That is, they will occur farther to the east of existing disturbances due to the fact that energy propagation will tend to be eastwards away from existing disturbances. Synoptic scale Rossby waves again can be seen on weather maps, as we've seen here, where we see an eastward propagation of the mid-latitude weather systems, as advection by the mean flow tends to dominate for these systems.